Hi! In this lesson we are going to talk about code profiling. Code profiling is one of the most basic, yes most important steps in the hardware design flow. The profiling is helpful in multiple cases. Most of the times, the code we want to accelerate does not fit completely in the hardware accelerator once it is completely optimized. Secondly, when it does fit, it may not be worth it to accelerate all the parts of the code it is composed of, as some function may not benefit from an FPGA implementation. Also, it provides information regarding what are the most computationally intensive parts, if any, of the algorithm we are considering. In the previous lessons, we have seen that the SmithWaterman algorithm is mainly composed of two parts. The first function takes as input two strings, called the query and the database, and outputs two matrices that are necessary for the successive steps. The second step of the algorithm takes the direction matrix as input and outputs how the query aligns to the target database. If you do not remember how the algorithm works, I suggest you to take a look at the lesson regarding the SmithWaterman algorithm. Now that we have recalled the structure of the SmithWaterman, let's see how we can profile a naive version of this algorithm. For this example, we use Vulgrim to profile our application. Vulgrim is an instrumentation framework that, paired with CallGrind, can be used as a call graph generating cache and branch prediction profiler. In order to profile our application, I already tuned some parameters, as the scoring system, inside the source code. The first profiling I will perform is specifying a query size of 256 randomly created characters and a database composed of more than 1 million characters. One thing that we have to notice here is that it is very important to use significative datasets when profiling the application. Otherwise, we may obtain results that are not significative. Now, let's take a look on how to launch Vulgrim to profile the application. First of all, let's compile our SmithWaterman code using GCC, the C compiler. Awesome! We have our executable. Now we can call Vulgrim, specifying that we want to use CallGrind as a tool. Let's specify the executable, its parameters, and we press Enter to start the profiling. In the example, N is used to specify the query size, while M is used to specify the database size. The profiler can take some time to benchmark our application, depending on the complexity of the algorithm and the size and type of the dataset we are providing as input. Once the profiling is complete, the tool produces in the current folder a file called callgrind.out, plus a number that is different at each call of the tool. Now that we have this file, we can call kcachegrind to interpret the result and analyze the call graph. In the bottom right part of the screen, we can notice the call graph of the execution of the program. Let's zoom into the call graph in order to analyze it better. The call graph is a control flow graph, where each block represents a function of the program. And the arrow starting from block A to block B represents that function A calls function B. In the example, function compute_SmithWaterman is called by the main function. The percentages in the chart represents the percentage of time spent by the function in executing itself and the function that it calls. In your opinion, what is the most compute-intensive function of compute_SmithWaterman? This one was easy. It is the compute matrices function. It takes, in fact, 83.78% of the total time of the program. Consider that compute matrices takes almost the same percentage of time of its caller, compute_SmithWaterman. Wait a second, there is something strange here. Where is the function performing the second step of the SmithWaterman algorithm? In order to understand a little bit more about what happened here, we need to come back to the tool and now focus on the left part of the screen, that is where all the functions are shown. Here we can find the Traceback function. In this part of the tool, the profiler provides us with multiple variables. In particular, it gives the user information regarding the cost of the function itself, or self-cost, the cost of the function including all called function, or inclusive cost, and the number of times the function is called during program execution. The reason why the traceback function is not included into the call graph on the right is that its cost is less than 1% of the total execution. Let's try now to profile our application using a smaller dataset by setting the query size to 128 characters and the database to 1024. Profiling with this dataset, we may notice as the cost of the traceback function increases to 0.40%, suggesting us that its impact is greater with smaller datasets. As a final confirmation, we can profile again our application, keeping the same query size of the first time and increasing the size of the target database. This final profiling confirms us that compute matrices is the most compute-intensive part of the algorithm and shows us again as the impact of the traceback function is almost zero when we use bigger datasets. Thanks to this profiling step, we now know that it is not worth it to accelerate the second part of the algorithm, as it is fast enough to be executing on a general-purpose CPU. It is very important to understand that not all the parts of the algorithm will benefit from the hardware acceleration, and being able to understand how to split the computation will allow us to extrapolate the best performance from our algorithm. In the next steps, we will focus on implementing and optimize on the hardware accelerator the first function. We will perform a stated code analysis to our code in order to identify its operational intensity. Then we will exploit the Berkeley roofline model to predict system performance.